Hello everyone, my name is Theo Wisniewski and my presentation today is going to be on the optimization of front view suspension geometry. So the question then is, why look at front view suspension geometry? So the WashU racing team, which does the Formula FSAE competition here, uses a short long arm type suspension geometry, and one of the typical starting points is looking at the front view geometry when designing the front suspension. So the objective function that I looked at when optimizing the front view suspension geometry for both the front and the rear suspensions was looking at the total lateral load transfer per G of acceleration. So when the car is cornering, how much force is transferred to the exterior wheels. So this equation here is taken from race car vehicle dynamics and is the total load transfer. And each of these variables is dependent on the front view design variables, which I'll talk about in a moment. So the list of design variables is given here on this slide. There are 18 total design variables, 4 points with X and Y coordinates for both the front and the rear suspension, as well as the track width for the front and the rear suspension, which is the distance between the two tires along the width of the car. So next I just want to talk about a couple of the linear constraints. So looking at lower and upper bounds for the 4 design points and the track width. This is to essentially give constraints based off of where things can or can't be on the actual vehicle. The next slide deals with a couple of more detailed design constraints that have to do with the geometry and placement of the roll center as well as the front view swing arm length, which are shown in this picture on the right here. This slide deals with, specific to the front view geometry for the front suspension, steering characteristics. So kingpin inclination, which is the angle basically from the vertical to the 2 points 1 and 3. And then the scrub radius, which is the distance from the tire center line to where that line intersects the ground plane. Alright, so the real question is, how did I go about solving this optimization problem? So I solved it using MATLAB code where I set the constraints, and then first off I used the genetic algorithm function with 20 iterations to find a valid geometry and attempt to remove local minimums. Then, once I had that result, I used that as initial conditions for fmin_con to search the constraint problem for the minimum near the GA's results. This slide here shows some of the results from that MATLAB code. The first picture on the left shows those lower and upper bound constraints, as well as the points 1 through 4 for the front geometry. The upper right picture shows the steering constraints, so kingpin inclination as well as scrub radius. Then the lower right picture shows the roll center height, which is what helps determine the lateral load transfer of the car. This slide shows similar pictures but for the rear geometry, showing the lower and upper bounds as well as the roll center height. And it also shows the side view roll axis, so it's got the roll center height from the front and the rear as well as the center of gravity location. So the conclusions to be drawn from this is that it is able to optimize the suspension geometry, but what I'd like to look at is using the different genetic algorithm options to ensure that a global minimum is reached. And then moving on into the future, you can adjust constraints to design geometry for different applications or for different vehicles. And then it can also consider other things such as loading in individual members of the suspension as well as component weight to have possibly a multi-objective optimization function. So thank you very much, and thank you for watching.